Hi everyone, so we're moving on to looking at particular types of chemicals called acids and alkalis. So before I do that, I just wanted to bring some keywords to your attention that I hadn't done with you yet. We've seen this reaction at the top. This is two hydrogen molecules and an oxygen molecule reacting to form two water molecules. When I'm talking about the word molecule, I mean more than one atom joined together. Okay, they don't have to be the same. So these are both element molecules. This is a molecule of a compound, but you can see each one's got more than one atom in it, and they're chemically bonded, so we would call them a molecule. So because hydrogen goes around in pairs, as I just mentioned in my previous video, H2, it's a hydrogen molecule, same with oxygen. Now this reaction is oxidation essentially. I'm going to talk about that again in a second, but I just wanted to point out these keywords. So the things on the left hand side of a chemical equation are called the reactants. Okay, the things that are going to react, they are the reactants. And on the other side, the thing that is made, we call the products. There might be more than one, or there might just be one product. Like in this case, there's one product, which is water. So reactants on the left and products on the right. Okay, a reminder of a few key things that I've already covered. So I'll just whiz through these. The first one at the top here, metal plus oxygen makes a metal oxide. Okay, and I said, where's my pen gone? I'll get the other one out. I'll put it away. I said to you at the time that I was doing that these form bases. Okay, and we're going to get onto that word shortly. Okay, you can get a non-metal plus oxygen. It's also called oxidation. It's still the same type of reaction, but you don't get bases. You actually get acidic substances. Okay, so second one is our displacement reaction, metal A plus metal B, salt. So long as metal A is more reactive, it will kick metal B out of the way. So metal A will scoot in there, metal B will be left alone. So we'll end up with a metal A salt and metal B being kicked out in a displacement reaction. The way to work that out, as I've said to you already, is to look at that reactivity series. That brings me on nicely to reactivity, the likelihood of something reacting, and also how vigorously something will react. And as I said, we've talked about the reactivity of metals already. Some metals are really reactive, will react very vigorously, and others won't react at all. So there is a kind of step-by-step series of them going from the most reactive to the least reactive. We've talked about the salt names, and I've just realised I've done something old-fashioned here. I've spelled sulfate with a PH. Now the general rule of thumb now is that they've changed the spelling of this. Sorry about that, although it doesn't actually matter, you can still use either, and I seem to interchange them, which I probably shouldn't do. I've been trying to stick to the F, but I've just spotted this mistake, sorry. Chloride as well, and nitrate. Okay, we've talked about these salts. You can whack a metal name in front of them. So magnesium sulfate, magnesium chloride, magnesium nitrate are all names of salts. We're going to come more onto salts in the next few lessons. Element then, a substance made of all the same type of atom, like a lump of gold. If we looked at that, all of those atoms in there would be gold atoms. We wouldn't get any other types. A compound is where you do get more than one type, and the key thing there is they are chemically bonded together. So the air is not a compound just because it's got all the different gases in. There are some gases within the air that are compounds. For example, carbon dioxide, or CO2. If we were to look at that and we could see the atoms, we would see one carbon and two oxygens, but they would be bonded together, okay? And so that would make this a compound. Also, incidentally, as I've just mentioned molecules, it's also a molecule because it's got more than one type of atom in it. Okay, so we're going to move on to look at what we mean by the word acid and what we mean by the word base and alkali. So what is an acid? You've probably heard of some acids before. You probably know that they can be quite dangerous chemicals. So they're a type of chemical compound. Okay, so they are made of different types of atoms. Concentrated acids are very corrosive. Now I've put this symbol on, we did do it at the very, very beginning of year 7, you may have forgotten it. This means corrosive. Okay, what that means is the substance, acid in this case, is able to actually burn through things. So very, very strong acids will burn through wood, they will burn through people's hands. Okay, so we need to be really careful when we're dealing with very concentrated acids. Now most of the acids that you would see in a lab at your level would have this symbol on. It's a warning symbol to tell you that there are hazards attached to this and to be alert, but it's not going to be, you wouldn't be dealing with anything with this on because this is too dangerous. Having said that, not all acids are dangerous. There are plenty of acids that are weak acids, such as vinegar, citrus, fruits, milk even are all acidic substances, and they're more than fine for you to eat and drink. Okay, so it isn't the kind of rule of thumb that all acids are dangerous. It really is about how concentrated, and we've talked about this word concentrated before, how strong, how much acid there is compared to water within an acid. And we talk a lot about dilute acids. We talked about dilute as well back in the last topic. Remember, to dilute something is to add water. So most of the acids that I will use, and certainly the ones that you would use if you had been here, are very diluted. They've got the acid in, but they've also got a lot of water. So I've got here a little beaker of hydrochloric acid, relatively strong compared to what you would use. You would probably use about probably about a tenth of this that I've got here, and I've got that straight out of the bottle. But even so, that is still quite dilute compared to some of the other acids that we might use. Okay, so all you need to remember really is that they are potentially hazardous and that they are a chemical compound. Now, in contrast to that, we kind of talk about bases, which are almost the opposite of acids. And when we start looking at the pH scale, which I will talk to you about in a video coming up, then this will make much more sense. But they're at the opposite end of the spectrum. Okay, now it's something that is able to react with an acid and neutralise it, and we'll do a whole video about the neutralisation reaction. What it means is, if you add an acid and a base together, you end up removing both the acid and base aspect, and you end up with something in the middle, which we call a neutral substance, which I'll talk about in my next video. So what are they usually like? Well, they're usually metal oxides, which we've met. We looked at magnesium oxide last week when I made that white powder. There's an example here, copper oxide. Those are basic, that's what I was saying last time. Things that make metals, metal salts, and metal oxides tend to be bases. Metal hydroxides, we haven't really talked about that, but I've given you an example, sodium hydroxide, because that's the one that I tend to use a lot, or I will be using in the coming videos. Hydroxide just means it contains hydrogen and oxygen within the compound. Okay, we don't need to worry too much about that at the moment. And then thirdly, we've got metal carbonates, and here's an example, calcium, the metal carbonate. Again, you don't need to worry too much about carbonates, we're going to come on to those, but they contain carbon and oxygen as well. So hydrogen and oxygen is a hydroxide, carbonate is carbon and oxygen in that compound, oxide just oxygen. Okay, so they're all different types of compound. Now, most bases, or a lot of them certainly, are insoluble. Again, a word that we did in the last topic. It means that it's not able to dissolve, okay, and particularly not in water, okay? But if they do dissolve in water, which some of them do, like sodium hydroxide, then we start to use a different word, which is alkali. So when I'm talking, this is one I made last time. I made this last week. This is a bottle of sodium hydroxide. Some of you watched me do it through the window and were very unimpressed. You can see there's my hazard labels on there. So this is sodium hydroxide, and I made it through a dilution method, so I added water so that it's not as strong as it was originally. But it's dissolved in water. It started off as solid pellets and now it's in a water form, so therefore it's an alkali. Okay, it is a base as well, but base could be solid or could be anything, liquid, gas. If it's dissolved in water, if it's a liquid, then we would call it an alkali. So they're basically the same thing, but this one's in a liquid form. And everything that I use from now on in terms of alkalis and bases are going to be in liquid form. So I'm going to be using alkalis. Now we tend to find them in soapy substances, so things like hand washes that you might put on your hands, absolutely fine. The stronger they get, the more unlikely you are to put them on your hands. They're in things like bleach as well, and then we have the really strong concentrated ones as well that we would have in a lab, sodium hydroxide being the main one that we would use, amongst others that you might use at GCSE and at A level. So types of acids and alkali, well, I don't know if I'm going to fill all of this in, but I'll give you a few examples. So acids that are very weak acids and quite harmless are things like lemon, so we could have milk as well, vinegar, and then we've got some really strong acids, so they would be all fine to drink or eat, but you certainly wouldn't want to be drinking things like this, hydrochloric acid, which is the one that I'm going to use probably most in the next few weeks. We've also got sulfuric, I'll try and remember the F, there we go. Sulfuric acid, I'll use a few times in the next few weeks. Nitric acid, I'll write it down, but we're not actually going to use it. Other things, battery acid that you might get in the battery of a car, very, very strong. You've got acid in your stomach, it happens to be hydrochloric acid. Loads and loads of examples of acidic substances, ranging from the very safe to the very, very dangerous. Okay, the more concentrated the acid, the more dangerous it becomes. Alkalis then, more likely things like cleaning products, soaps, bleach, I suppose that's also a, how do you spell bleach? Also another one. The one that I'm going to keep coming back to, so it's just worth remembering it, sodium hydroxide. You can work out, if you're feeling really bright, what that's got in it just from the name. Sodium is the name of metal, and I said hydroxide, hydro, hydrogen, and oxide, oxygen, of varying strengths. Okay, so the other thing about these ones in particular, hydrochloric acid, sulfuric acid, nitric acid, sodium hydroxide, is that we can make them different strengths. So you can have a weak version of sodium hydroxide. You can also have a very strong version, which we would call a concentrated alkali. Okay, I'm going to leave that there. I'm going to set you a few questions to do alongside the gas test, which you should have already watched. And then that's it for today. And we'll move on to how do we know if something is an acid or an alkali in the next video. Okay, nice to see you. Bye-bye.